So I'm Buddhika, and so my undergraduate research was on laser engineered fatigue response of flexible interconnects. So I did this research under Dr. Alma, and so before diving into my research explicitly, let's go through what is flexible electronics, because it is rather relatively new field. So flexible electronics are basically electronic circuits that are manufactured on flexible substrates. So those substrates may be polymers or plastic flexible substrates, and they have some requirements which are being flexible and durable, which are as given, because this is flexible electronics, right? So they have to be flexible. But rather than that, they have to have this quality of having little to no mass but adding to the system. So another thing is that the ability to be power DC. So that means if we are giving any voltages or currents to a flexible circuit, they have to be given in such a way that the circuit does not become too bulky. And also it has to be able to communicate with the users and the environment more efficiently and more easily. So let's see how manufacturing of these flexible electronic circuits works. So there are two main components of a flexible circuit, which are the substrate and the conductive material. So the substrate is basically a flexible substrate, mainly created from some kind of polyester or polymer, some hydrocarbon or carbon structure. Right? So polyester means just our day-to-day polyethylene terephthalate and polyamide. Those are the main substrates that we use in our laboratories. And also there are commercially available inks which are used to manufacture these flexible electronic circuits, and we use these inks and we can use technologies such as deposition and printing technologies in order to connect the substrates and the inks together. So there are two main types of fabrication in flexible electronic circuits. So one is deposition. Deposition has three main types. One being chemical deposition, which deposits the inks or the conductive material on the flexible substrates using electrolysis or some chemical reaction. And also there is physical deposition, which is we use some kind of physical force or some spray coating. We just deposit it physical. So spin coating uses the centripetal force to deposit the inks more uniformly, and Dr. blading is another very famous method, and also spray coating. So when it comes to printing, it is a rather novel method than deposition, where it is very easy and cost effective compared to deposition methods. So mainly we use inkjet printing and aerosol jet printing in our low scale projects, and we use screen printing and roll-to-roll printing for large scale flexible electronics projects. So in my research I use inkjet printing, which is very reliable yet very cost effective method. And after printing those electronic circuits, we have to do a process called sintering. So what is sintering? It is basically let's say those metallic inks that we use, they have like organic solvents in them. Those organic solvents are like not conductive, therefore they hinder on the metals ability to conduct electric signals. So we have to like heat our samples, that means our circuits, locally or using some method below the melting point of the used nanoparticle inks, so that the bonds are stronger. That means the metallic bonds become stronger. The nanoparticles fuse together, and also the solvents to be evaporated. So that results in better conductivity and the better adhesion among the substrate and the nanoparticle ink. And also, since the metal is connected together very well, there is less ability to be oxidized. That means like if there are metal oxides, that means the ability to conduct electricity reduces as the same as if there are organic things. Also, like the pose means that since we are using nanoparticles, they are in an array like this when it is printed. So there are small pores inside each particle in the neighborhood. So when we heat the printed electronics, those pores become reduced because of the beta adhesion. So the pore reduction helps with reliability, because these pores are the thing that causes mechanical breakdowns in circuits. We will look at that down the road. Yes, that is mainly my research. So there are lots of methods in sintering the flexible electronic circuits. So the most conventional method is thermal sintering, where we just use a conventional oven and we enter the substrates and the printed materials inside the oven and keep the oven on for a few hours under constant temperature. But there are a few drawbacks in that, because the plastic or the polymers that we use as substrates have much low temperatures of glass transition. So that leads to deformation and stuff like that if we are to heat into much higher temperatures. So in order to overcome that drawback, the scientists have found out localized heating methods such as laser sintering, where we use a laser and we focus it on substrates, the printed samples, and that causes localized heating, which results in the organ solvents being evaporated more quicker and more efficiently. So that is a very popular method right now. And another one is electrical sintering, where we give an electrical pulse to a circuit from two ends and let the Joule heating take care of the heating element, and it will cause the solvents being evaporated. Also, there are a lot of methods like photonic sintering, where we use intense light, and also plasma sintering. So what happens in sintering is shown here. So if you can see here, this is an image of scanning electron microscope image, where it is just printed and left to cure under ambient conditions. And this is after laser sintering. So if you can see here, there are like big pores, right? There are huge gaps over here and here, here and here. But in here there are like no huge gaps. There is just one here, and others are very small. And we can see that the bonding is even better. I don't know if it is clear, but the particle size is also a bit larger because of the greater bonding happens. So after this sintering process, we arrive at a circuit like this, right? So there are like many printed parts of a flexible electronic circuit. It can have maybe a small display. If you are familiar with like organic LED or OLED displays, those can be printed. And energy harvesters, that means things like solar cells and antennas where we can gather signals, sensors, and also batteries and capacitors, transistors. In the current age, we can print them, but unfortunately, we still don't have ways to print high performance chips. So they have to be added externally using any conductive adhesives. So yeah. Also, another important thing I would like to point out is that these lines, if you can see, so these lines go from major components to chips, and they connect each and everything together. So those are called interconnects. So those are the things that I was focusing on during my research, right? Because they are rather thin and brittle. When a flexible electronic circuit goes through like bending and complex forces, those are the things that break down first, right? Because they are very brittle. So we have to be able to overcome that problem using some methods, right? So that was what I was focusing on. And those electronic circuits, flexible circuits, have lots of applications right now, and they will grow more in the future. So let's see some of the examples where we can have like advanced medical devices which are together with our skin, right? And also sensors that are integrated inside our body which can monitor our health, and also like smart clothing and e-skin, which is used in even like soft robotics, if you are familiar. And also we already have mobile phones that are like foldable, right? So this is the technology that they are using to create flexible displays. And also we have applications in powering, such as improved solar cells and capacitors, and also sensors. There are numerous sensors, such as, well, in our lab we used to develop gas sensors and salinity sensors by my colleagues, my friends. So there are lots of research to be done, and that brings us to the pros and cons of flexible electronics. So the cons are mainly due to it being a rather new field, and there haven't been done many research on how to improve. The pros basically says on geometries can be like, we can't use a rigid circuit on like our skin, right? Because our skin is flexible, but we can use a flexible sensor or something like that, right? And also it can have like, can withstand bending and stress, right? So mechanical resistance is very high compared to like normal rigid circuits. And also they have very limited maintenance, where we install a flexible circuit and it just works. You don't have to work with the format. But to set up flexible electronics, there is a high initial cost because we have to buy the inks, buy the substrates, and get a printing method started, or deposition method, and also we have to create a better sintering method, and that has a high initial cost. Also, if one part of a flexible electronic circuit breaks down, then it is rather difficult to replace it because the whole circuit is printed. So that means we will probably have to replace the whole thing rather than being able to repair or add modifications to it. Also, the reliability issues which I talked earlier occurs because of those pores and void structures that are in the printed surfaces of conductive inks. So those cons are what we are looking at in our research. So as I told you earlier, we are focused on developing sensors and cost optimization for if we take commercially available inks, they can be quite costly. So if we can create them or manufacture them in our labs, they can be comparatively cheaper. And also we are working on reliability and predicting the failures. Even in my research, I am focusing on that. So those are the main fields of research, and you can see that the popularity of flexible electronics has been improved since the beginning of the 21st century. It has shown an exponential growth. Right? So that means there are a lot of work being done and yet to be done. And so if you are interested, you can always talk to Dr. Akmal and get started on flexible electronics. Right? So with that, I think we are ready to dive into my research, which focuses on flexible interconnects, which are, as I told you guys earlier, one of the most important parts of a flexible electronic circuit, because they are the ones that are carrying signals and connecting all the main parts together. Right? So there can be different types of interconnects. Some can be straight, and some can have bends in them, and some can be curvy. All of those interconnects have to be manufactured using the same technology, right? As we discussed earlier. So in my research, I used inkjet printing method to print my interconnects, and then use the laser and focus it on the interconnects to sinter them, and then use those samples for gathering data and drawing conclusions. Okay. So, as I told you earlier, the interconnects go through very complex processes. It can be twisting and stretching and bending, and even over time they go through like these process over and over, and it causes it to the interconnects to develop cracks on their surfaces. So that means the middle conductive case cracks from the middle. And those start as like very small cracks, micro tears we call them, and they develop further and further until it causes the interconnect to completely break up. So it is important to predict that fatigue or failure point, because if we know that point earlier, then we can take actions to replace or maybe modify and keep it from failing, right? So that was my objective in the research, where I used mainly lasers, and I had to fabricate those interconnects with predetermined, that means predicted fatigue response. To explain that a bit further, if we take an interconnect and we can manipulate its sintering parameters basically. So if we are using laser, then we can manipulate laser power and how fast it is sintered and how many times is it sintered. Using those conditions, I wanted to show that the interconnects can be developed into having a predetermined lifetime. So let's say if we are talking about stretchers, so I wanted to manipulate those laser parameters and develop an interconnect which had, let's say, 1,000 stretches. So that is what we call fatigue life. And by developing that method, I wanted to develop a method to monitor the health of interconnects. So it means the quality of interconnects in real time. So those were done using the effects that laser sintering parameters have on the fatigue level. So I had to analyze those in order to. So my approach was to use 3 interconnects in parallel. So one being the main interconnect, right, and the other 2 being auxiliary interconnects. And my focus was using a critical interconnect which had the most lifetime, and then the auxiliaries having smaller lifetimes than those. So let's say if one had, the critical interconnect had 1,000 stretches in it, then the other 2 might have had 500 and 800 stretches in it. So their fatigue life will be 1,000 and 800 and 500. And my hypothesis was that under the same conditions, those 2 will accumulate the same number of stretches. So it is kind of intuitive. So when we use that in a circuit and analyze the resistance increment over time, and understand that the third interconnect is failing, that means the system has accumulated 500 stretches. So that means the life of the critical interconnect has been reduced by 500. So that means 500 and 1,000, that means 50% quality is remaining inside the interconnect. Right? So that was my hypothesis, and let's see how I approached my problem. So this was how I did it. So basically, first I designed these interconnects with determined length of 80 millimeters and width of 0.2 millimeters, which is not stated here. And then they were printed using an Epson L130, very cheap, cost-effective desktop printer, which is available at the market, in the market, and it was printed on PET substrate. So after printing, this was my sintering setup, which is here is the laser, which was Cobalt 0801 laser, and its wavelength was 785 nanometers, That means it is near infrared or infrared laser, and it was guided through these mirrors and focused on my interconnects here using a convex lens. So this is a more closer look at those interconnects under. You can see this is the laser. So this here is a CNC machine which was used to scan the interconnect completely under the focused laser beam. This shows how I align my interconnects with the path of the laser, and the signals were given using a universal G-code center software to manipulate the CNC. And after sintering, each and every sample was mounted on this fatigue cycling setup, which is the bending setup. So this is how it was mounted. The resistance was analyzed real time while it is being bent. Right? So this it starts from here and goes up to here. So the interconnect is over here. It is bended by using a 2-inch mandrel. So that means radius of bending is 2 inches, and this was done over time, and the real-time resistance change was recorded using a digital multimeter to my lab. And those data were analyzed using multiple methods, which were experimental and computational both. So first, I did the electrical characterization using those collected resistance data from the digital multimeter and analyzed how the resistance changes, and also the crack formation was analyzed using SEM images and digital microscope images. Also, some simulations were carried out to show whether the interconnect was completely sintered, and some statistical analysis was carried out to determine optimized parameters, laser parameters for sintering. So we will discuss that in more. Let's discuss a bit about how efficient this laser sintering is. So in the left is the resistance of an interconnect which was cured under ambient conditions. So that was just kept in the lab, and the real-time resistance was analyzed. And then this here is resistance under laser sintering. So we can see that to reduce the resistance by 35%, under ambient conditions, it took more than close to half an hour. And under laser sintering, it was done in like nearly 20 seconds. And also, even the reduction is larger compared to the cure. So this is closer look at the image that I showed you before. So this is under 20,000 magnifications, and you can see even clearly the larger pores in the cured interconnects electron microscope image compared to laser sintered image. So we can determine that laser sintering is a good method of sintering. Alright, so this is one sample of results. This is just a single interconnect bent over like 700 cycles. In red is the maximum resistance during a single bending cycle. The bending cycle, as I explained, was the machine going up and downwards. And the maximum resistance occurs at the top because that is where the maximum bend and maximum stretch occurs. So the line in grey or black is the one where the resistance was recorded at the rest position. So that means the interconnect is at rest, no bendiness. And the blue data points are the average resistance over a cycle. So average resistance means the complete data over a cycle was taken and the average resistance was calculated for that data. And we can see that it has a more linear trend compared to the red, which is the maximum resistance. It is more linear and also has less noise. And also it shows a significant increase than the resistance at rest. So I selected this average relative resistance increase, or average resistance increase, as my response to carry out my analysis. And this shows how laser power has affected the change in resistance. So we can see that the lowest power, or the power in 350 millivolts, has the most stable, has resulted in the most stable interconnect. Right? It has fatigue life. So fatigue life was defined as 10% increase of resistance. So here you can see that it is like 2.5% at 700 cycles. So the counted value for 10% was 3850. But other powers resulted in like different lifetimes compared to the 351, but there is no correlation among those two. So for my critical interconnect, as I mentioned earlier, I selected this 350 milliwatt power parameter, and then to select auxiliary interconnects, I had to do some more work. So moving on, this is the temperature simulation results, where I confirmed that the temperature increment is uniform for most powers, for all the powers that I use. This is the morphological analysis, where I took samples from interconnects and then analyzed them under the digital microscopes. And if you can see here, there is a very liberal crack almost to the interconnect, and here is a very small crack which is under 50,000 magnification, and these are called micro because they are very small, and these are the ones that keep developing. And so these are some more cracks that are caused by the bending. When these cracks form, we say that fatigue has been reached. And then to find out the auxiliary interconnects, or the parameters to use for auxiliary interconnects, I had to use a process called design of experiments. So design of experiments is a statistical approach. If you are familiar with statistics, I think you have heard of this. But if you have not, then it is basically like linear equation, but for multivariables. Multiple variables have to use. So I use laser power, scanning speed, and number of scans. And my result or response is the average relative resistance increment. So average resistance increment after 2500 bending cycles. So what I wanted to do here was find out an equation relating to the ARR value with these two parameters. So if we say A, B and C, we have to get a function of F, A, B, C related to ARR. So we use combinations of these. So we first select two levels, lower and upper level. Since we had 354 my critical interconnect and it showed very stable lifetime, and 450 showed the least lifetime and 550 was the second highest. So these two were chosen as the levels for laser power. And scanning speed was chosen as 5 millimeters per second and 15 millimeters per second. The number of scans 1 and 10. So combinations of each of these levels was taken and samples were sintered using those parameters, and then the ARR after 2500 bends was recorded. And using those data, I did the DOE analysis, and it led to finding out that the laser power is the largest contributor to the response. That is really intuitive, because laser power is what governs how much heat is transferred to the interconnector. And then it was found out that scanning speed also has a comparatively large effect, because scanning speed dictates how long the heat is being supplied. So after that, the number of scans was proved to be very less effective. As you can see the effect curve as well. So it did not have a contributing effect for the body. So to conduct or to create the equation, we just have to use this blue color A, B. So these are pretty equations. So ABC means the combined multiples of these two parameters, these three parameters. Also BC, scan speed and number of scans. And using that equation, I predicted or I calculated the auxiliary parameters as these. So I have used this 500 milliwatt laser power and 10 millimeters per second scanning speed with 10 scans for 12% increase after 2500 bends. And for the other auxiliary, for 23% increase, it was predicted that 450 milliwatts and 15 millimeters per second with one scan was sufficient. So that here the critical target was 6.5%. So that means after 2500 bends, the resistance will be increased by 6.5% and 12% and 23% respectively. And this is the result of those three resistances for those three parameter sets. And you can see that the green color, the line is the auxiliary one, which has the most increment, and so on. So finally, this was my result. After real analysis, I achieved almost inside the predicted values. So for the critical I predicted 6.5, but I achieved 4%. That's even better. And for auxiliaries, I achieved very close at increments of resistance. So these are the fatigue lifetimes, and those can be used to gauge the health. Fatigue was, as usually, it was set to 10% resistance increment, and this was the number of brain cycles it required for achieving the 10% increment. So, when these three were in the same environment, and it was fatigue tested, once this auxiliary one fails, that means close to 1000 bends have been achieved, and that means the health of the critical interconnect is at 80%. And when the second auxiliary fails, that means 2200 bends have been achieved, and the health of the critical interconnect is around 50%. So that led me to conclude that this method can be used to determine method to gauge health real time using parameters of laser sintering. But the interesting point here is, if we we have to have the same conditions. If we are doing this in a different lab, the parameters might be different, because we can't really predict the printing, which is a drawback, because we can't predict whether the printing is always the same. So that is basically what I did. So the first part of my research was published as an abstract in the American Physics Society virtual March meeting. And so it was presented virtually. So this study was done under our department, and I had help from our supervisor and our research labs, and our laboratories, and our staff, and my friends. So thank you very much. If you have any questions, you can